what you need to do is build on that concept. We started at the very beginning looking at what? Not even balancing. Oxidation numbers. So your first step for every one of these problems is determine the oxidation number for every single element on every side of the equation, or both sides of the equation. All right, so we would go through and start with our oxidation number for manganese, or that manganese plus 2, our manganese ion. What is the oxidation number for that manganese? How do you know it's plus 2? Not because it says. Its overall charge is plus 2. If we went through to solve for the oxidation state, it's 1, because there's one element, times the oxidation number. Okay? The oxidation number, by definition, will equal plus 2. So it is a little bit more straightforward, but we are still officially solving for it. In the product, what was our oxidation number for manganese? We'll go through the same process that we've done before. There's one manganese times its oxidation number plus 4 oxygens. The oxidation number for oxygen? -2. How do you know it's -2? It's your rule. What is the overall charge on this molecule? That's the -1. Upper right-hand corner is always the charge, not the oxidation number. Whoops. We can then go through and solve for x, and we would get x being equal to positive 7. So our oxidation number for our manganese is plus 7. Oxidation number for sodium. How do you know it's plus 1? So on the product side, I will give you that. That is plus 1, straight out of the gate. On the reactant side, how do you know it's plus 1? What kind of a compound is this? Ternary ionic. Because sodium is a metal, which means I can split this into the ions. What charge is sodium? Plus 1. So really what I'm looking at in this equation, or this problem, is that I have sodium plus 1 and BiO3 minus. How do I know BiO3 is a minus? Because sodium's a plus 1. What's the oxidation number for sodium now, or sodium ion? 1 times X equals plus 1. Okay, questions on that? Really? Nobody.
So we need to know it's an ionic bond and then look at the charge on each
You
ion.
would need to recognize that this is an ionic bond. Are you expected to know that this is an ionic bond?
Yeah.
Chapter 6, yes, you are expected to know that this is an ionic bond. Okay. This is why you had all those rules, why we talked about those already. You are required to know that this is an ionic bond. Okay. So this gives us our oxidation state for our sodium being plus 1 on our reactant side, and on our product side it's plus 1. The next atom that we'll look at, just because it's easier, oxygen. Oxidation state is -2. Why am I not calculating anything? That's one of our rules. The oxidation state for oxygen is always a -2, unless it is by itself. It is not by itself here, so we don't have to worry about it. The last one, kind of run out of colors. Bismuth. How do we solve for the oxidation number for bismuth? Remember, this was an ionic compound. This is bismuth O3 minus. How many bismuths? How many BIs are there in that formula? 1. We don't know its oxidation number. Plus 3 oxygens with an oxidation state of -2, which equals -1, the overall charge on that molecule. We can go through and solve for x, and we get x equal to +5. Go ahead.
Why is it equal to 1? There's not a negative sign above the... Yeah, but in the equation.
In the equation there's not, but remember, what are we looking at when we look at that equation? It is an ionic compound. In an ionic compound, we have ions. Sodium is a +1. Why is sodium a +1? It's always a +1. You're required to know that from chapter 6. Okay? If sodium is a +1, what does that necessarily make BiO3? It has to become a -1. That allows me to simplify my formula down, and I've now broken that into BiO3 as a -1 charge. I can then evaluate for the oxidation number of bismuth, which comes out as a +5. You'll notice that I am not saying 5, okay? And a lot of people are shouting that out. Is there necessarily a difference between +5 and 5? No. They're both meaning the same thing. I go through and put the extra emphasis that it is a +5 because that positive is a sign issue. If we somehow accidentally start dropping our signs, we could potentially mess everything up. So I always try to include the sign in my oxidation number. So we simplify all of that out. The oxidation number for our bismuth becomes a +5. As a check, because we just did some goofy stuff with the sodium, I think that's bismuthate. You're not responsible for that name, so don't stress about it. As a check to make sure that we actually did that correct, if I take all of these charges, or sorry, those oxidation numbers, and I add them up, what should it equal? 0. Why? The overall charge for that molecule is 0. So I add +1, +5, and -2, and I get not 0. What happened? There's 3 oxygens. So it's a +1, +5, +3 times -2, which equals, now it checks out as 0. So it did indeed work. Okay? How are we doing with that so far? Accept silence as an okay. Okay. Bismuth in the product. How do you know it's a +3? It's one of those trivial ones that directly solves out of the chart. Okay. So what we've now gone through and done is assigned all of the oxidation numbers. So the next step in this is then deciding what happened in the course of the reaction. So let's take a look at our manganese. What happened to go from a +2 to a +7? What happened to the manganese? I don't want to jump directly to oxidized or reduced. What I want to start with is what exactly happened to it. It lost electrons. Okay? So I would write that down, loss of electrons. Mathematically, that is a minus for our loss times the charge on an electron, which is a -1. Minus times a -1 is positive. So if my value becomes more positive, I've lost an electron. We'll go through and do the same thing with our sodium. What happened to the sodium? Nothing happened to the sodium. Oxygen. And our bismuth, it gained electrons, which is mathematically a plus times a -1, which gets us a negative value. If our value gets smaller, we have gained electrons. Dagnabbit, I knew that was going to be a problem. Okay. Questions on that so far? Okay. Now what we can do is move to oxidized and reduced. A loss of electrons means oxidized. Okay, this is from our Leo. A gain of electrons is reduced from our GER. Okay. Last part that we could stack on top of this would then be in reference to the agents. Okay. Our agent is always going to reference our reactant. Okay. Manganese, Mn+2, was oxidized. So if it was oxidized, it caused something else to be reduced. So our Mn+2 is known as the, way to use that really weird one, which I never use, but okay. Reductant, ANT, or our reducing, there's our ING agent. Is that counterintuitive? Absolutely, because it was the species that was oxidized. But it comes back to what the definition of a reductant is or a reducing agent is. Okay. What does that mean our bismuth ends up acting as? If it was reduced, it was our oxidant with our ANT, or our oxidizing, there's that ING agent. Okay. All of this work is our complete and final process as far as what you guys are really expected to be able to do with an equation this complicated. Okay. So what kind of questions could I ask on an exam? What is the oxidizing agent? To figure out the oxidizing agent, you could potentially go through and have to solve every little piece here. Okay. Do you really? Your agent, by definition, is a reactant. How many reactants are there? 2 of them. So if you start off this whole question, you go, well, I want to figure out the oxidizing agent. I'm going to look at manganese. You assign the oxidation number to manganese. It's +2. You look at the oxidation number of manganese in the product. It's +7. That doesn't say oxidizing agent yet. It doesn't say anything about agents yet. Okay? +2 to +7 means what happens? Lost electrons, which means oxidized, which means reducing agent. But the question that was put forth was, we need the oxidizing agent. Process of elimination, there's only 2 possible valid answers for your agents. They have to be reactants. If it's not Mn+2, it has to be the other one. You're now done. You don't have to go through and solve all the rest of that. Kind of makes sense?
So the whole thing NaBiO is the...
Which brings up the next question. What is our agent? Our agent is the species that was put into the reaction to cause everything to occur. Was Bi+5 added to the reaction? No. What was added to the reaction? Sodium bismuthate, NaBiO3. That is the agent. What was that? You don't have to repeat that. That's okay.
So can you repeat that? The agent is the species?
The agent is the species that was added. Okay. Not the element that did the chemistry, but the species that was added. The species that was added will contain the element that did the reaction or did the chemistry. Okay? What if I had instead asked for what element was reduced? Let's say we did all of that work. We still did the manganese. We came out and saw that the manganese was oxidized. Well, if I ask for the element that was reduced, I know it's not the manganese. Do I know it was sodium? Not yet. Not until I solve to see what happened to the sodium. Do I know it was the oxygen? Not yet. Do I know it was the bismuth? Not yet. I'd still have 4 possible answers. Why? It comes back to the question. The question asked, what element Okay? You have to be very careful with the question being asked. The agent refers to the species. An element refers to the element, just the atom that's changing. Okay, so be careful with the question asked and make sure you're answering the question asked to the level of specificity that it is requiring. Okay? Questions? Are there tricks within this? Should we ever deal with oxygen? Why ignore oxygen pretty much every time you see it? It's always a -2. The exception, when it's by itself. And you will see it by itself as O2. Why O2 and not just O? Oxygen's a diatomic element. So if you see O2 just chilling by itself, it's being involved in the redox reaction. Okay. Any other time you see oxygen in a compound, ignore it. It will be -2. You don't have to worry about it. Okay? Other big tip-offs in general that you're looking at a redox reaction. Okay. This last one, we don't have a big tip-off. We have to go through and solve it. But that middle one, huge big hint screaming at you. Just looking at the equation, it says this is a redox reaction. That big hint is right here. And in particular, comparing it to right here. On the reactant side, that copper is what? Its elemental state. In its elemental state, what's its oxidation number? 0. Did it change? Yes. This question must be a redox reaction. Okay. So we can simplify the question all the way down. You could just be given 3 or 4 or 5, I guess we have 5 possible answers. I give you 5 possible equations and say, which of these is a redox reaction? Look for things in their elemental states, because if they're in their elemental state, it's redox. Okay. It's a big, big hint. You don't have to do anything with oxidation numbers because you've already picked out the element or the reaction that's going to be a redox reaction. The one caution on that, maybe I give you 4 reactions and the 5th answer is all of the above or none of the above. Okay. So watch out for those extreme cases, particularly if I say which of these is a redox reaction. If you looked at these 3, said which of these is a redox reaction, you go, oh, this one, copper in its elemental state, must be a redox reaction. You bubbled that in as an answer. Is this reaction a redox reaction? Yes. So is everything else. Okay? So be very leery of those all or nothing answers. Okay? Questions on that? A lot of information gets stacked here. What you have to do is go through and slowly process it, do a couple problems, break it down exactly as we went through and did here. If you go through and do that breakdown, you'll probably find within 3 questions, it's not that bad. You actually kind of understand what's going on, and you can start to see shortcuts. Okay? Until you've done that practice to get used to those patterns, do not use shortcuts, because they will screw you over every single time.
Do we have to balance the equation before figuring it out?
Balancing the equation is what comes next. As far as our redox reactions go, you will not have to balance any as complicated as that last one. Okay. The first one, fair game. And in fact, the next 2 down, you don't have to worry about. If you have to move into 152, that's when we add in a whole new set of rules on balancing redox reactions that gets a whole lot more complicated. You don't need to worry about that yet. If you don't have to take 152, don't worry about it. All you got to do is the nice, simple, relatively simple balancing that we'll talk about now. Other questions? Okay. Those were all our answers. Balancing our redox. So what we talked about on Tuesday, that first equation, okay, we can end up balancing that one relatively quickly by dropping a 2 in front of that H+. And everything balances out nicely on its own. Standard balancing rules that we've been using. If we go through and look at the next equation with the tin and the iron, our standard rules, how many tins? 1 and 1. How many irons? 1 and 1. According to our standard rule set, that looks balanced. As soon as we move into redox, we have to take into consideration other things that are changing in the course of the reaction. Those other changes are the number of electrons. How do we monitor the number of electrons in a reaction? The charge. Look at the charge on the reactant side of the equation. So all we're going to do is take the sum of all of those charges and total it up. What do we get? Plus 5. On the product side, what do we get? Plus 6. Is the charge balanced? No. That necessarily means that my electrons aren't balanced. Well, electrons are matter. If this is our balanced equation, then we somehow messed with our balance of electrons. In fact, in this case, we destroyed an electron. Okay? We can't do that. Laws of physics prevent us from destroying matter. Okay? So there has to be something else involved in this equation to allow us to balance it. The way to go through and do that goes through and looks at half reactions. So we will take our reaction and we will split it into the two halves. We refer to our reactions as redox. Why? Half of the reaction is reduction. The other half of the reaction is oxidation. So what we're going to do is split into those two parts, our reduction half and our oxidation half. So we can take a look at our tin and say, what does tin go to? We'll take a look at our iron and say, what does our iron go to? And what we should end up with is these two equations. Right? And now what we will do is ignore half of the equations. We'll just look at one. So just look at the reduction. Is the reduction balanced? No, because of charge. So we're having an issue with our electrons. We need to balance out the charge. So what we will now do is introduce that electron as a balancing agent. Where should I place the electron? Okay. I heard reactants and products. So guess what I'm going to do? I'm going to put it on the product side. Okay. To balance, one of our last steps in balancing is to do what? Check your work. What's the charge on the reactant side? What's your charge on the product side? Plus 1. Did I get closer to it being balanced or further? Further, which means I'm wrong. I put the electron on the wrong side. Yeah, we'll do it this way. So that means I can now put my electron on the other side. What's the charge on my reactant side? Plus 2. Charge on my product side? Plus 2. It is now balanced. Yes, I've introduced an electron. Okay? But I need that electron to balance the equation. Okay? That electron has to come from somewhere. It doesn't just come from nothing. Where does it come from? It comes from the tin. Okay, so now we can move to the other half of the equation. And when we look at the tin plus 2, we want to go through and balance that reaction now with electrons. Where should we place our electron? Okay. I actually heard in front of it first, so I'm going to put it there first. Tough. What's the charge on our reactant side? Plus 1. Charge on our product side? Plus 4. Did we get closer or further from balancing? Further, which means placed it on the wrong side. As a big hint, if you balance the first one correctly by putting the electron on the reactant side, guess where it needs to go on the next reaction? The opposite side. Okay? Because one case accepts electrons, the other case must get rid of electrons. So our electrons will show up as a reactant and a product in the course of the reaction. So if I now go through and place my electron on the reactor, that's the product side, but you knew that already. What charge on the reactant side? Charge on the product side? plus 3. I am closer to balancing, but it's not there yet. What do I have to do? Add another electron. Okay. Which will then take my charge to plus 2. Now my charges are balanced. Is it valid to go through and write plus an electron plus an electron? Yeah, perfectly fine to go through and do that. But can we simplify that? Yeah, we can simplify that to saying just plus 2 electrons. Okay? With these half reactions, we split them apart. Okay? If we can split them apart, we can put them back together. So let's add these two equations up and see what happens. Okay? I got 1 electron on the reactant side and 2 electrons on the product side. So what I can do is group the terms. I can subtract 1 electron from both sides of the equation, just like we would do with math, okay, or algebra. Which then means what happens? How many electrons do I have left over on the product side? 1 electron. 2 minus 1 is 1 electron. If we add our two equations up, we get this fun little equation. Is our charge now balanced? Yeah, it is balanced. Cool. So we could say, well, now here's our answer. Except, what's the issue with electrons? They are incredibly high energy and not stable. They cannot exist on their own. So I cannot use this equation, because this equation is now telling me that an electron just comes out and says, whoop, I'm here. Doesn't happen. It must be consumed by something. So when I add my two equations together, I have to make sure that when I look at my final product, I do not have any electrons left over as a product, and I do not have any electrons starting with as an excess. They must entirely cancel. Right? They never show up in a balanced equation. Whoa, don't look at that. How can I ensure that when I add those two equations up, that the electrons entirely equal each other on reactant and product side? I need to make sure I have the exact same amount of electrons on both sides. If I went through and made this 2 a 1, that would mean they canceled, except I have to cut the electrons in half. Well, if I have 2, that's fine. Can I cut 1 iron, or that's not iron, 1 tin atom in half? No, it would no longer be tin. So I can't cut the bottom reaction in half. What will I end up doing? Doubling the top reaction. I will make sure that I don't have 1 electron in the top reaction. I have 2 electrons in the top reaction. Okay? So yeah, that's now 2. And if I added them up, sure, my electrons cancel. But where did that second electron come from? We have to multiply the entire equation by 2. Not just the number of electrons. Because if we now look at that first equation, is that first equation balanced? What's the charge on our reactant side? Plus 1. Charge on our product side? Plus 2. As soon as we make that a 2 electrons, our equation is now unbalanced. So if I change my electrons by multiplying by 2, what do I also have to do to the irons? Multiply them by 2 as well. So I would, whoa, come back here. 2 electrons, 2 irons, 2 irons. Ooh, that's a lot of numbers to be changing. I sure hope that didn't affect the balancing of my equation. What's the charge on my reactant side? Plus 6 minus 2 gets me a plus 4. Why is that plus 6? There are 2 plus 3 irons. Product side, what do I have? Plus 4. Do my charges balance? Yes. Since my equation is now balanced, I can now add that to my tin equation and see what I get as a result. Since I stepwise all this. When I add those two equations together, I see electrons show up on both sides. I can subtract 2 electrons from both sides. What happens to the number of electrons? They disappear from the equation. Negative 2 electrons plus 2 electrons is 0. Okay, so the electrons cancel out. I now add my two equations together. The 2 from our ions translates down in my total equation, and I end up with a new equation. Is this equation balanced? How many ions do I have? Reactant side. 2. How many ions on the product side? How many tins on the reactant side? How many tins on the product side? 1. So the atoms are balanced, so that's okay. What about the charge? What is the charge on my product side? Sorry, reactant side. We have +6 plus 2 for a total charge of +8. What is the total charge on my product side? +4 plus 4, and I have +8. Atoms balanced, charges balanced. I now have my final balanced equation. How does this get asked on the test? Given the equation up top, what is the sum of the coefficients in the balanced equation? If you look at the equation up top, that looks balanced, so we would say our answer would be 4, except is that equation up top balanced? No. You have to go through and balance out the electrons, and your answer is actually 6. Okay? Questions on that?
Do we have to go through that entire process, or can we balance it the same way we balance just regular equations?
How do you balance regular equations?
Not sure if I can define it.
When we balance regular equations, we count the number of atoms on each side. How many tin atoms on the reactant side?
Well, I guess I mean the numbers.
Yeah, you have to look at charge, and charge is dependent on electrons.
Yeah.
So can you blindly change numbers to match up the charge on both sides? Yes. Absolutely fair game. So you could eventually work your way through and get that without looking at the half reactions, without looking at electrons. You are pretty much blindly guessing. And an equation this simple, yeah, you could probably guess through that pretty quickly.
More complicated.
Okay? And the more complicated ones, it becomes much more difficult. Okay? There's one more way I can ask this question. How many electrons are transferred? If you do not evaluate your half reactions, and you look only at our top equation, so I can say how many electrons were transferred. And because you just suggested a guess and check method, we'll take a look at the guess and check method as well. Okay. You look at the top equation. How many electrons do you see? Do you see any electrons? Remember, an electron is an E with a negative symbol next to it.
None.
None. So how many electrons are transferred? Looks like none. If you now guess and check your way through on balancing it to make sure your charge matches up, how many electrons do you get in the properly balanced equation? None. So your answer, you would say, is none, and you'd be wrong.
Right. I knew it was coming.
Okay. How many electrons were transferred in the course of this reaction? Look at your balanced half reactions. What did tin plus 2 do? It gave up 2 electrons. What did it give up those 2 electrons to? The iron. Hence it absorbed those 2 electrons. Tin plus 2 transferred 2 electrons to iron plus 3. How many electrons were transferred in the course of the reaction? 2. And you see that from looking at the balanced half reactions. Okay? Some of you may say, well, I could have just looked at one of those reactions. Yes, you could have. Let's say you blindly guessed and said you looked at iron. How many electrons to balance out the iron equation? Only 1. So you still get the wrong answer. You have to balance both equations to see how those electrons come out. Okay? One question. One question. Okay? Last one. Take your time. I want to say vastly more complicated, but it is more complicated than the previous one, okay, the previous example that we looked at. So when we go through and look, the first thing we'll do is split into our half reactions. Okay, so we've got aluminum going to aluminum plus 3 and copper plus 2 going to copper. How do I balance the first equation? I'm going to assume that you said add 3 electrons to the product side. Why'd you have to add 3 electrons to the product side? You need to balance the charge on both sides of the equation. Aluminum start at 0. Plus 3 will cancel the 3 electrons, and we'd have 0 and 0. Okay, are we good with that? We can now move to our copper. Copper plus 2 to copper. Is that balanced? No. To balance it, what do I need? I need 2 electrons on the reactant side. Here's your trick. When we add these 2 equations together, my electrons must cancel. Okay. They canceled previously by multiplying one reaction by 2. Why did I multiply the one reaction by 2? So that 1 electron times 2 is 2 electrons, which balances out with the other electrons. It was a single multiplier that worked. What can I multiply 2 by to get 3? And it has to be whole numbers. You can't multiply it by anything to get 3, okay, as a whole number. So what we have to do is find the common multiplier between 2 and 3. What is a common multiplier between 2 and 3? 6. How do I make the 3 equal to 6? Multiply by 2. How do I make the 2 a 6? Multiply by 3. I can now add the 2 equations together. The electrons cancel out, and I'd have my proper full balanced equation. Okay. Do we need to look at the full balanced equation with the question that's being asked? How many electrons were transferred? 6. I don't need to balance this out or add those 2 equations up, because I now see that I need 6 electrons to be consumed on one side, 6 electrons have to be produced on the other, which means 6 electrons are transferred. I don't need a full balanced equation. How would I change the question to make sure you need a full balanced equation? What is the sum of the coefficients of the balanced equation? And we would end up with, for a final answer, 2 plus 3 plus 3 plus 2, 10. So depending on the question asked, you're going to have to do differing amounts of work. It all goes back to going through the whole process and trying to decide what's going on within each of those steps. Okay? You may be confused by this at this point. You need more practice. We can't sacrifice more practice in class, unfortunately. Okay? So if you've got questions, ask about it after class. I'm more than willing to help out.
With the top one, if you balance the...
Does the top one need the half reaction method? No. Okay, you can balance that one straight normal like we've done before. Don't have to worry about it. What is the big difference that triggers you to say, ooh, I need to do the half reaction method? Charges. As soon as you see charges, you should be going, okay, I have to split this into half reactions. Okay. Without the charges, you don't need to worry about it. You can go through and balance as normal. Okay? That is the end of Chapter 17 as far as we're concerned. We can then move back into Chapter 7. We'll look at our double replacement reactions. The general format for our double replacement is as shown up here. I did try to color code, and I think I did it successfully, where blue represented the cation and red represented the anion. So in our double replacement, what we are doing is just exchanging those ions to look at a new product. When you do that exchange, you have to be careful of the subscript numbers associated with each of your reactants and potentially products, because that subscript may take on different meaning in the course of your writing. So let's take a look at our first reaction. Aqueous barium chloride reacts with aqueous potassium chromate. What is the symbol for barium? What is the symbol for chloride? Is that formula correct? AQ, good call. Still not correct because barium's a +2, chloride's a -1. For that formula to be correct, I need to have 2 chlorides. Nomenclature is still important. Reacts with, what does that mean? Plus aqueous potassium chromate. Symbol for potassium. K. Symbol for chromate. I know it's not one I told you to memorize, but CrO4. Charge on chromate, I'll tell you, is a -2. Potassium, +1. Is that formula balanced? No, what do you need? 2 potassiums. Whoops. Aqueous. This will then go to our products. It's a good thing I wrote really, really big. I now have no space. I will have barium with chromate. Oh, son of a frick nuts. And I will have potassium with chloride. I will not have K2Cl2. Why not? Why is there a 2 next to the chloride in our reactant? To balance barium. Why is there a 2 next to our potassium? To balance chromate. Why do I not include the 2 in our products? Those are already balanced. Why did I transfer the 4 then? The 4 is what makes that chromate. Okay. Just because we have a subscript number doesn't mean it carries the exact same meaning. The 4 in chromate is part of the formula that makes it chromate. Just like the A in barium is part of what makes that symbol barium. If I removed the A, it now becomes boron. If I remove the 4 from our chromate, it becomes something other than chromate. I don't know what it is. Something other than chromate. Okay? Interesting part of this is you notice I have reacts with in quotes for both of these. Okay? Why do I have reacts with in quotes? There could be ones that don't react. How would we know a reaction occurred? Activity series isn't a bad idea, but the activity series applies to metals. None of these are in their metallic state. In a broader sense of term, our activity series applies to single replacement reactions. These are double replacement. I can't apply the activity series. How else would I know, in general, that a reaction occurred? Phase change. If I see gas form, how else? Solids form. Okay, again, change in phase. You're technically correct. Okay. So, how do I know the phase of either of these species? Good point. You don't yet. Okay. Do the next one. Aqueous sodium chloride becomes NaCl, aqueous. Everybody gives me a hard time for my Cl, so let me try that again. Cl, right? Plus aqueous lithium nitrate. Nitrate's a -1, lithium's a +1, so that's balanced. This goes through in our double replacement. I'm going to be slightly obnoxious here. I'm going to write it as lithium chloride plus sodium nitrate. Questions? Hold it. Okay. Hopefully you guys should have gotten through and done that all the way through. Okay. I did forget to put in one part, as was astutely pointed out. I forgot to balance the equations. Officially you are responsible for still balancing, so let's go through and check that. In our first equation, how many bariums on the reactant side? 1 and 1. Chlorides? 2 and 1. How do I fix it? I put a coefficient 2. Remember, I can't change the subscript. Potassiums? 2 and 2. I'm now out of space, so I'm going to erase all of that. Chromate and 1. My equation is now balanced by that simple addition of that coefficient. If we look at the bottom one, sodiums, 1 and 1. What's the other one? Chloride, 1 and 1. Lithium, 1 and 1. Nitrate, 1 and 1. Should you be balancing that fast? Absolutely, you should be balancing faster than that. Okay? You should be getting to the point of inspection, which means you look at it, you did all that work in your head. Yeah, sorry, that's where you got to be. So, yes?
Why isn't that on the second one, the C and B come first before the A and B?
I was waiting for that question. Why in our equation? So if we take a look at what I did up here on that first equation, what I exchanged was B and D. Just like the double replacement formula shows. In the second equation, what did I exchange? I exchanged the location of A and C. Oh my gosh, I must have done something wrong, right? Addition is communicative, meaning it does not matter the order in which I write them. I could have just as easily written the sodium swap first. Okay. Does that make sense? Okay. Back to our original question. How do we know the phases on our products? Yes, that's an interesting choice. I'll tell you right now. How did I know all of those three, or those three species, were aqueous? I have a rule memorized that allows me to tell that those three are aqueous. That rule happens to be any group 1 element in an ionic compound will always be aqueous. Lithium is group 1. Sodium, group 1. Potassium, group 1. I have that rule memorized. I kind of expect you to memorize that rule too, because it's really straightforward. Okay. The rule that I don't expect you to have memorized is the phase for barium chromate. The phase for barium chromate ends up being a solid. So now let's look at these two reactions and decide, did a reaction occur in both? What did we see happen in our first reaction? Barium chloride was aqueous, which means it is dissolved in water. I have a solution. Potassium chromate is aqueous, another solution. I mix two liquids and what do I end up with? A solid. What does that mean? Reaction has occurred. Bottom one. I mix two solutions and I end up with two solutions. Officially, it's not two solutions because they're mixed. Right? So I have two solutions and I ended up with one new solution that looked exactly the same. Any phase changes? What does that mean? No reaction.
Why didn't the phase change occur?
The phase change didn't occur because we know those phases. Okay, we'd have to look at our solubility rules to predict what those phases are. So ultimately, you knew how to read a solubility chart to tell you those phases. Okay? I do not expect you to be able to predict by looking at any random formula and saying, oh, well, that compound should be soluble in water. Not yet. Save that for the end of this semester. Okay? To predict the phases, you need a solubility. Oh, there we go. Yeah. Come on. Solubility rules. Okay? Your textbook gives you a bunch of solubility rules. This is their format behind it. You are responsible for being able to interpret and follow it. Okay? The ones that I highly encourage you to memorize would really be these first three, which I've actually grouped as just one thing in my head. And yeah, that's it. I only have those first three memorized. Why would I memorize those first three and none of the others? It's not even most common. No, sort of easiest to remember. What is different about those first three as opposed to every other rule in that chart?
They don't have exceptions.
The first three have no exceptions. Everything else has an exception. Okay? I'm not going to waste my time trying to memorize exceptions to rules. It's just a waste of life. Okay? It's not a very good rule then. Okay? Are there more solubility rules? Yes. There's tons of them. There's also tons of exceptions to those more rules. Okay? You are responsible for interpreting the rules given to you. Those first three are helpful to have memorized because when you see them pop up, you can immediately say they are soluble and you don't have to worry about it. Okay? So let's go through and look at it for our barium chromate. How do we know that that is a solid? Well, we could go through our list and say, where is barium? You go through and look through that list, it's going to be kind of hard to find barium, though it is up there in a couple spots. Okay. I would argue that what you should be looking for in this list are not the cations, the metals. You should be looking for the anions. Hydroxide is negative. Sulfide is phosphate, chromate, sulfate. Oh, that was sulfide. Sulfate. They're all negative. So instead of looking for barium, look for chromate. Where's chromate on this list? Rule 7. Okay? In our Rule 7, it is under the category of being generally insoluble in water, which means if I see chromate ion, I should be saying solid every single time, except when Rule 1 applies. Okay? Is barium Rule 1? No. Barium is in group 2, not group 1. Barium will be a solid. Kind of makes sense? Questions about that? Cool. Last reaction is our neutralization reaction. Okay? It is defined as the reaction of an acid with a base. Okay? It is a double replacement reaction. You will find that all the questions I ask will follow this same general format. So let's take a look at a question here. The neutralization of sulfuric acid with potassium hydroxide. I'll give you a minute. Do it on your own. Sulfuric acid. It says acid, so we know it to be aqueous. We also know it has a hydrogen. How do we know that this is HSO4 and not HS?
It doesn't have hydro.
It does not say hydro. This is a ternary acid, which means it's a complex ion. It has to be sulfate, okay, as our ion. The charge on sulfate is -2. The charge on hydrogen +1, which means I need 2 hydrogens to balance out the sulfate. Potassium hydroxide, written up just as normal. Potassium is a +1, hydroxide is a -1, that's balanced. We can then go through and predict the products. I'll have potassium with my sulfate, and I'll have my hydrogen with my OH. Okay, why do I need 2 Ks? Sulfate is a -2, potassium is a +1. For my equation to be properly balanced, that K needs to become 2 Ks. It needs to be K2SO4. If I go through and look back at the beginning, my hydrogen, there was 2 of them. Why do I only show 1 hydrogen by itself here? +1 for my hydrogen. Hydroxide is a -1. That formula is balanced as is. Now that I have my proper formula, I can go through and balance the equation. To balance the equation, you'll notice that we need to do that. We'll need 2 potassium hydroxides to produce 2 HOHs. Anybody have a problem with HOH? That is also known as water, H2O. Why did I write it as HOH?
It's easier to
Actually, it's not to confuse you.
To keep OH together.
It's to make it more obvious to see the double replacement reaction occurring. Right? Hydroxide is staying as a complete unit. That will help with the balancing process if you decide to balance as complex ions as opposed to the atoms. Okay. Did a reaction occur? Well, it's a double replacement, so we could go back to our solubility rules. Potassium sulfate, soluble, insoluble. Soluble, because potassium is group 1 metal, so I would write aqueous next to it. How about HOH? That's water, so what's its phase? Aqueous, that's an interesting. You're telling me water is dissolved in water? It doesn't really make any sense to say that. It's really a liquid. Did a reaction occur? Yes. I have formed a compound. I have formed liquid water when there was no liquid water, which means the amount of water in my solution should increase. Will I be able to see the amount increase? Probably not. How do we visualize this reaction having occurred? This is an acid-base reaction. All acid-base reactions are exothermic. Remember that ACS video where they poured the concentrated or the water on top of the concentrated acid and they said, oh my gosh, look at how violent and messy this reaction is. Because at a really large scale, mixing an acid and a base is very exothermic. It can actually release enough energy to cause water to boil. So by mixing those two, we release a ton of energy. How would we visualize that in the course of a reaction? Do we have any kind of device to measure the release of energy? A thermometer. Yes. All you do is put a thermometer into your water and watch the temperature rise. The other thing you could do is a really fancy device. Touch the container where the reaction is. If it gets hot, there's an exothermic reaction. Okay? Again, it's going to require practice going back and forth with these. One of the last things that I want to get through, which means I'm going to skip through a couple slides here, we will come back to them, is the concept showing up in Chapter 8 and Chapter 9. Ultimately, those are one and the same general idea. Chapter 8 introduces one new concept. That one new concept is a mole. That's it. That mole allows us for a conversion factor. Now that you have a conversion factor, guess what you get to do? Convert like crazy. So everything we did back in Chapter 2 with all those conversions now comes back to haunt you because you are doing that now with a new unit that you cannot physically wrap your brain around. That's actually why we invented the mole as a unit, because we can't actually comprehend the size of a mole. Okay? The reason behind all of that is just to go through and process so that we can do an experiment with measurable quantities of things. Okay? So ignore that. If we took a look at Lego Hogwarts, how many Lego bricks went into that building? A lot. Okay? So we could go through and count every single brick, or we could start to simplify that and say 20,000. Well, by saying 20,000, really all you were writing would be 20,000. What does that number mean? 20,000. Okay? That is peanuts in comparison to a mole. Okay? I'm not even going to attempt to draw the zeros on a mole. I'm back here. 1 mole is now a really large number of things. Just like 1,000 means 1,000 of an object. A mole means 6.022 times 10 to the 23rd of those objects. Okay? That's all it means. Okay? It is a way to count the number of things. It tells you nothing about mass. It just tells you how many are present. Okay? We can then use that to predict and use things or get things to a proper value to measure. What is the mass of carbon? 12.01. What's the unit? AMUs. That is the atomic mass unit. To convert atomic mass unit or to go to a balance, do we weigh in atomic mass units? No, we'd have to convert that into a gram unit. Anybody know that rough gram equivalent? Be it 12.01 times 10 to the negative 19 kilograms. Negative 19. Our balances record to 10 to the negative 3. Negative 19. We can't mass that. It is physically impossible for us to do that on our balances. Okay? I'm not even sure we can do that on the planet yet. Okay? We don't have that capability. So if I'm going to run an experiment and I want to know something about how many atoms are present, I need to scale up and instead of reacting a single atom, react a whole bunch of atoms. So instead of reacting just 1 carbon, I'll react 2 carbons. So now it's 24 times 10 to the negative 19. Okay? Or 2.4 times 10 to the negative 18. That's better. Okay? So let's add a third one. Okay? Now it's 3.6 times 10 to the negative 18. I still can't weigh it. So add a fourth, add a fifth, add a sixth. Okay? What we end up finding is to get it to a measure or a value that we can actually use and manipulate and weigh on our balances, I don't need 4, 5, 6, or 100, or 100,000. I need 6.022 times 10 to the 23rd atoms. That number is massive, stupidly huge. Think of our debt, not even close. Okay? This is ridiculous. We can't even comprehend our debt. We turn our debt into a trillion value because now it doesn't look as big because we don't have as many digits attached to it. And that's only, what, 9 zeros? This is 23 zeros. Huge. But that's because atoms are that tiny.
19 trillion.
Okay? 19 trillion? Okay.
Be 20 trillion before he leaves office.
Okay? Massive, massive number. All that is a way to count a large number so that we can convert our numbers on our periodic table to something useful. The number, our mass number on our periodic table, will now become, for pretty much the rest of the semester, not AMUs, but not moles, because moles is not a mass. Moles is the number of atoms. It's going to be grams per mole. So I'm now going to take 6.022 of carbon atoms times 10 to the 23rd carbon atoms, and if I weigh that, that will weigh 12 grams. The periodic table now gives me a very important conversion factor, the ability to convert the number of atoms to a mass. Huge. Science, yes. We could turn that into a meme, but that would be inappropriate for right now. Use the mole conversion, start working in chapter 8, because we really only have, I think, 3 more lectures before the exam. Okay? It's all going back to looking at our equations and just doing conversions, finding where that information is stashed. So here's one more summary and then we're done. Come on, where is it? There it is. Conversion factors and where to find them. Okay? Measurements. You're required to memorize some of them. The rest will be given to you. The number of atoms, we can find that in a formula. How many atoms are in sodium sulfate? Did I say sodium atoms?
You just said atoms.
I said number of atoms. Sorry. Number of atoms in sodium sulfate. Well, there's 2 sodiums, 1 sulfur, and 4 oxygens. So we add that all up and I would get 7 atoms. How many sodium atoms are in sodium sulfate? 2. Right? So our formula gives you the number of atoms. Number of molecules. The number of molecules comes out of a balanced equation. Does it have to be balanced? Yes. That's why we did balancing. Number of moles. That's that 6.022 times 10 to the 23rd. Atomic or molar mass comes from your periodic table. If you think back to exam 1, please, you can leave, that's fine. If you think back to exam 1, there was that question where I gave you a whole bunch of conversions. All of those conversions now are not given to you. You have to be able to read the question and find those conversion factors either on the periodic table or in a balanced equation. That's where you're at. All right, so I will start whatever